Okay students, so now we'll start with the actual modern physics part. So the first topic which we'll be learning in this chapter would be photoelectric effect. So it was basically proposed by Einstein in 1905. So let's understand what it is. So it basically tells that it is basically a phenomenon of light which is that whenever light is incident onto a metal surface. So what we observe is that some electrons come out of that metal surface. So that phenomenon is what we name as photoelectric effect. So it is pretty simple. So whenever we have a surface of a metal, so let's consider this as a metal surface. So if this is the metal surface and if light is incident onto this metal surface in this manner, so you all know that the energy that the light possesses is in the form of chunks of energy, pieces of energy. It does not come as a continuous flow. So it comes in this manner in the form of small packets of energy. So now when light is incident on that metal surface, so what happens is that when these photons go and strike that metal surface, some electrons come out of that particular surface. So that process is what we call as photoelectric effect, and now we will be learning about why that happens, how that happens and all that. So let us first define photoelectric effect. I will maybe write it down over here. So it is the phenomenon where when light of sufficient energy is incident on a metal surface, electrons are emitted. And these electrons which are emitted during this process, so when this light strikes, these photons go and strike the metal surface. So some electrons come out, and these electrons which come out, they are called as photoelectrons. Okay. So this is what is basically the idea of photoelectric effect. So now let's understand how this happens and what happens when photons go and strike an electron and all that. So before we know about all that, there is also one more definition which you should be aware of, which is very important for the further analysis, and it is basically work function. So every metal will have this value already defined for it. So work function basically means the minimum amount of energy that will have to be supplied to an electron so that it can be removed from the metal surface. So if let us say we have this metal surface and there is a electron over here, which is, I have told you earlier that metals generally have free electrons in their volume. So whenever I have to remove that electron, free in the sense it is not inside, it is not bound to the nucleus, but it is still having some attraction from the nucleus. It is relatively easier to remove it. It does not mean that you can remove that electron without giving any energy. It is still bound to that material, but not completely bound to the nucleus to which it actually possesses. So anyways, that is a property of a conductor. So now work function basically means that to remove that electron from that metal, from that matter, from that bulk of material, the amount of energy that should be supplied to it is what we define as work function. So I'll write it down. It is represented with symbol phi. It is the amount of energy that should be supplied to an electron so that it can be removed. From a metal. Okay. So, that is how we define work function. So, do not get confused with the definition which you would have studied in chemistry for ionization energy. Ionization energy is also of this similar sort of definition. So, ionization energy is basically the energy that should be supplied to remove an electron from an atom of a gaseous system. So, whenever you have you have a gas, and if you take an atom in that particular gas, and if you have to remove the electron from the outermost shell of that, is what we call as ionization energy. So, that is completely different from work function. So, work function is defined as the energy required to be given to the electron, which is in a material, which is in a solid, which is in a metal surface, to be removed from there. So, both are completely different. So, now we know that for removing any electron, we need to give it this much amount of energy. Now, let us talk about how that energy should be given and what happens when that energy is given. Now, before we learn about that, there is one major thing which we will have to be aware of, is how a photon interacts with electron. So, what I mean is, whenever photon goes and strikes an electron, what happens there? How does the interaction behave? So, this is very, very important. So, what happens is that, let us call it like this. So, you can understand it in a very simple way. We can say that the photon electron interaction is something like this. It is either all in or nothing. So, let us remember it in this manner, all in or nothing. What I mean by that is that, so whenever a photon which has some energy, it is a packet of energy, it goes and strikes an electron. So, this has energy and the electron requires energy. So, keep that in mind. Now, when this photon goes and strikes the electron, so the interaction happens in this manner. It is either all in or nothing. So, it means that the photon will either give its complete energy to the electron or none of that to the electron, and when none of that is given to the electron, the photon goes and strikes and just reflects back with the same amount of energy, and when all the energy is supplied to the electron takes that energy and the photon is absorbed. So, there is no existence of photon after that. It is just like a balloon of water just falling onto the surface, and there is no existence of that balloon after that once it is broken off. So, it is something like that. So, the photon, once it strikes with the electron, it is absorbed by the electron, and the electron may use that energy in different ways. Now, keeping this in mind, let us see what happens when a photon goes and strikes the electron, whether photoelectric effect happens or not. Now, there is one very important thing you will have to be aware of here. So, hc by lambda is the energy that the photon possesses. Phi is the energy that the electron requires to be removed from the material. Now, we can say that unless and until this photon which strikes this electron has an energy of hc by lambda greater than phi. So, only when hc by lambda is greater than phi will we be able to remove this electron out from the metal. So, what that means is that the photon should have more energy than what the electron requires. Only then the photon may remove that particular electron. So, this is the basic condition for photoelectric effect to happen. So, if this condition is met, we can say that the photoelectric effect may take place. I am once again using my words specifically, I am not saying it will take place, it may take place, and the reason for that is something like this. So, there are two points which you will have to keep in mind. See, even when hc by lambda is greater than phi, sometimes photoelectric effect may not take place, and there are some reasons for that. So, what happens is that the first reason for that is basically collisions. So, let us think of a scenario like this. So, this is a sodium metal, let us consider. So, this is the metal surface, let us say it is Na, and Na has a phi value of 2.3 electron volts. So, which means if you need to remove an electron from the surface of sodium, you will have to supply that with an energy of 2.3 electron volts. Okay. Now, let us say light is incident on it, and that light possesses photons. So, you all know what happens if the photon has an energy less than 2.3 electron volts. Nothing will happen. So, photoelectric effect will not take place, and this photon which goes and strikes here will just get reflected back. So, if there is no sufficient energy, it just reflects back and electron cannot be removed. Now, let us consider this has an energy of 4 electron volts. Let us take a scenario like that. Now, this 4 electron volts of energy which this photon has will get transferred to the electron. Now, the electron in the process utilizes 2.3 electron volts to come from the bounds of the material, and it has an extra 1.7 electron volts. Now, it takes that 1.7 electron volts as a kinetic energy and it tries to come out of the material, but in that process it collides with the surrounding electrons or surrounding atoms, and it might lose some of that energy. So, collisions are responsible for this electron to come out or not come out. So, if like we have seen here, if that remaining 1.7 electron volts of energy, if it is completely lost during the collisions, then the electron will not come out. So, it has lost all its energy inside itself and it is not coming out. Now, based on this idea, there is also one more way in which the electrons, the photoelectric effect may not happen. So, these photons which go and strike the metal surface might not go to the position where electrons are present. So, what I am saying is that these photons might miss striking the electrons altogether. So, even in that case you will not observe electrons coming out of the metal surface. So, photons not striking electrons. So, these are two reasons why even if Hc by lambda is greater than phi, photoelectric effect may not take place. But keep in mind that for photoelectric effect to take place, this condition should definitely be met. What that goes on to say is that this condition is basically a necessary condition but it is not a sufficient condition. If this condition is met, it does not ensure photoelectric effect taking place, but this should definitely be there for photoelectric effect to take place. So, that is the basic idea. So, now let us talk about the mathematical logic behind this concept. It was basically given by Einstein in 1905, for which he has won a Nobel Prize. So, let us see that equation. It is called Einstein's photoelectric equation. Okay. So, photoelectric equation, so as given by Einstein, is something like this: Hc by lambda minus phi is equal to Ke max. So, a very simple relation. So, Hc by lambda is the energy that the photon possesses, and when that energy is absorbed by the electron utilizes phi amount of that energy to come out of the bounds of the material, and it has a remaining of Hc by lambda minus phi amount of energy, which appears as its kinetic energy, or to be very precise, it may appear as its kinetic energy. And the reason why I am saying may is because collisions can occur and it might lose its kinetic energy, and that is the reason why we have a max over here. So, this Hc by lambda minus phi is the maximum possible value of kinetic energy that the electron may possess. So, in reality we can say that the kinetic energy which the electron possesses while coming out of the metal can have any value between 0 and hc by lambda minus phi. I hope this is very clear to you. So, even though we are giving an extra energy of hc by lambda minus phi, the electron will not take that complete energy while coming out, because even though it gets that much energy, in the process of coming out of the metal, it might lose some of that energy or all of that energy. So, when it loses all of that energy, it does not come out at all, its kinetic energy is 0. When it loses none of the energy, it comes out with the maximum energy, which is this. So, this is the expression for maximum kinetic energy with which an electron comes out of a metal surface. Now, based on this, we will now understand an experimental setup which we use for photoelectric effect. So now we will understand the experimental setup which we use for understanding photoelectric effect. So, this is the setup which we have, and what you see here in the form of a cylinder is basically a tube, a cylindrical glass tube, which is vacuum sealed. So, everything inside here is, there is no material, there is no matter inside. So, what you see here are electrons, which I will explain in a while. So, this is a vacuum sealed tube, cylindrical tube, and it possesses two metals. So, this is one plain metal surface and this is another plain metal surface. So, they are connected through wires to a battery and an ammeter, which is used for recording the current established in that particular circuit, and we also have a switch to control the flow of current. Okay. Now, in this particular process, to observe, to understand photoelectric effect, what we do is we make sure that light is falling onto this particular metal surface. So, this end which is connected to the negative terminal of the battery is basically the cathode, and the end which is connected to the positive terminal of the battery is an anode. So, they are made up of different materials as well. Okay. Now, let us observe what happens when light is incident on this cathode. So, cathode is the one which behaves as the emitter. So, this is the emitter and emitter of electrons, and anode is the one which behaves as the collector. So, it is going to collect the electrons which come out of this metal surface. Okay. Now, so when light is incident, let us assume that the light which is incident over here is of sufficiently high energy. So, I am making sure, I am already assuming this condition, hc by lambda is greater than phi. Only under that condition you know that photoelectric effect will take place. So, assume that hc by lambda is greater than phi. Okay. Now, what happens here is that the electrons come out. So, because photoelectric effect takes place, electrons come out, but these electrons which are coming out, they have different kinetic energies with them. Some of them come out with very high kinetic energy, which is hc by lambda minus phi, we have just discussed earlier, and some of them will come out with very small amount of kinetic energy, because they would have lost most of the energy due to collisions while coming out. So, the electrons which are coming out will have a wide range of kinetic energies, starting from 0 till the value of hc by lambda minus phi. Now, we are going to now discuss about 3 different cases. Case 1 is no battery, and case 2 is the battery is present with a positive polarity, and case 3 the battery is present with a negative polarity. So, we are going to discuss about what happens in each of these scenario, what would we observe happening in this particular circuit. Okay. Now, let us first discuss about the no battery scenario. So, let us assume that there is no battery. So, light is incident onto this metal surface, electrons have come out, and some of them are having high kinetic energy, and as a result of that, because of the kinetic energy which they possess, they might be able to reach till the anode, and once they reach the anode, it collects the electrons and some electrons start flowing back to the cathode, and there is basically a closed loop of flow which is established over here. So, not all electrons will be able to manage to reach this particular collector, only those which are having sufficiently high kinetic energy, only those electrons will be able to manage to reach that anode, and only because of them we see a current which is established in this particular loop. So, even when there is no battery, keep in mind that even in the case where there is no battery, we can observe some current flowing in the circuit. So, the current is observed, and that current which we observe in that particular circuit is what we call as photocurrent. So, because the reason why we call it as photocurrent is because it arises because of the flow of electrons which are generated by the light, and it has nothing to do with the battery. There is no battery, there is no external source which is making the electrons move. So, electrons are being produced by the light, and those electrons are the ones which are moving in this particular circuit. So, that current which is established, the current which we observe flowing in this ammeter, whatever reading that it records, is because of the light which is producing it. So, that is the reason why we call it as photocurrent, photo meaning light. Okay. So, that is the idea. Now, think of this scenario, what happens? So, even when there is no battery, we are observing a current to be flowing in this circuit, because out of the electrons which are coming out from the cathode, some of them are able to manage to reach the collector, and because of which a current is observed. Now, think of a scenario of what would happen if I connect a battery over here. So, if there is a battery which is connected over here, what will happen? So, what does that battery do? So, we have discussed earlier that by connecting a battery in this particular way, with this polarity, so we are connecting this to the higher potential and this one to the lower potential, as you can see, and as a result of that, what happens in this region is that this one is at higher potential and this one is at lower potential, because of which an electric field is established here. So, an electric field is established inside the tube from the anode to the cathode. So, it would be in this particular direction. Now, what happens because of that electric field? We have already discussed earlier in our prerequisite concepts lecture that whenever electrons are in an electric field, the electrons experience a force opposite to the direction of electric field. So, which means when the electric field exists in this region, these electrons experience a force in this region, in this direction. So, those electrons will be accelerated in that particular direction. So, it basically means is that connecting a battery in this manner with this polarity actually helps the flow of electrons from this end to this end. So, now you can easily guess. So, because of connecting a battery with this polarity, what would happen to the current in the ammeter? It increases, because this battery, because of being connected this way, is making this as the higher potential end, and this higher potential is pulling the electrons towards it. So, these electrons are pulled, they are being forced to move towards this end, which thereby increases the flow of current in this particular circuit. Once they reach the collector, because of the flow, the path which is present over here, they are once again going to go and reach the cathode. So, that is what keeps the cathode neutral. Otherwise, think of this scenario, if there is no path, if these electrons which are removed from here are not getting back to the cathode, if that is not happening, this would always be losing electrons, and as a result it would get positively charged. So, that is not going to happen in this case. You can consider this as a neutral metal, because whatever electrons which it is losing from here are eventually going to come from the other side. Okay. So, that is what happens. So, when I connect a positive polarity here, I can expect the current to increase. So, that is clear for us now. Now, in the exact same manner, what happens if I can connect a negative polarity, which means if the battery is connected in this manner, if it is connected in this manner with positive polarity or higher potential end over here and lower potential end over here. So, what would happen in that scenario? And exactly opposite, electric field is now established in this direction, and as a result of that, the electrons which are coming out will be actually experiencing a force in the opposite direction. So, they have a velocity in this direction, but the force is actually pulling it back. They are not, the force is actually not allowing the electrons to reach the collector, and because of that reason you would observe a drop in the current. And sometimes if this polarity is very large, sufficiently large, what might happen is that this electric field might pull these electrons so strong that none of the electrons might be able to reach the collector. So, no, even the fastest moving electron, let us say the electrons are coming out from here with some velocity. So, different electrons will have different velocities. So, the ones which are faster moving are the ones which are going to reach the anode, but because of this electric field being strong, if it is strong, even the fastest moving electron passing through this tube will not be able to reach the collector. It might happen. So, what happens in this case is that in the negative polarity situation, so if the negative polarity is made more and more and more, there will be a point of time where none of the electrons which are coming out from the cathode will be able to reach the anode. So, they might just go here, stop here, because the pull backwards is even stronger. So, in that particular scenario you will observe zero current. So, even though photoelectric effect is happening here, those photoelectrons are not reaching the anode. So, you can't observe a current to be established in that circuit. So, we will learn about that. I will basically show whatever I have told you regarding these three cases on a graph, which is a very important graph as far as photoelectric effect is concerned, and the graph is like this. So, we would basically draw the graph between the current and the applied voltage, the current here representing the photocurrent, and V here representing the applied voltage. So, I am going to show you what would happen, the three cases which I have just discussed: no polarity, positive polarity and negative polarity. So, I will represent the whole thing on this particular graph. So, now this is the point where V is 0. So, even when V is 0, I is not 0. So, that is what we have observed in the no polarity case. Even when there is no battery, some electrons from the cathode will be able to reach the anode. So, even without the battery also there can be some current in the circuit. So, when the value of V is 0, let us say the value of I is this much. Okay. Now, we have observed that as I increase the voltage, as I increase the applied voltage with the positive polarity, so with the positive polarity, the electric field which developed in that scenario was helping the electrons to move further towards the anode. That is what we have discussed here. So, if the polarity was like this, the electric field was like this, and the force on the electrons was in this direction, and the electrons were pulled towards the anode. So, in that case we have understood that the current should increase, and that is what would exactly happen. So, the current increases. So, as you keep increasing the voltage, the current, the photocurrent in the circuit also increases continuously, but there is one important thing that happens here, which is a very important feature of photoelectric effect. After a while, if you keep on increasing the voltage, the current increases and increases, but after a while the current stops increasing and it becomes constant. So, the value of that constant or the maximum value that the current reaches before becoming a constant value. So, that maximum value of current is what we call as saturation current. So, that is called as saturation current. I will repeat once again. So, even when there is no battery, we will observe some current flowing in the circuit, because the faster moving electrons will be able to reach the anode, and as I increase the voltage, more and more electrons will be pulled towards the anode, and as a result you observe the current increasing. And after you increase the positive polarity to a sufficiently large value, which is somewhere over here, so once you cross this particular value of positive voltage, the current becomes constant. Now, understanding why current becomes constant is a very important feature in photoelectric effect, and most of the questions related to photoelectric effect would be based on this saturation current itself. So, we will understand that in a while. Let us also discuss this graph on the negative side. So, what happens when the voltage applied is having a negative polarity? Now, we have already discussed that when we have negative polarity, the electrons which are coming out are being opposed by the electric field. So, when the polarity was like this, the electric field was like this, and the force acting on the electron was like this. So, which means even the electrons coming out are experiencing with some velocity, they are experiencing some deceleration. So, they come out, but they start decelerating. So, they are losing their kinetic energy. So, in the process of losing their kinetic energy, they slow down, and even the fastest moving electrons, maybe some of them might be able to reach the anode, but most of them will not be able to reach. So, what you will observe is that when the voltage is negative, the current keeps falling down, because it becomes difficult for the electrons to reach the anode. So, you will observe that the current value of current drops down, and it keeps dropping down as you keep increasing the negative voltage. The value of current keeps dropping down, and eventually you will also observe that at one particular value of negative voltage, the current becomes 0. So, this is the value of negative voltage, this is the magnitude of that negative voltage. Let us represent that with V naught. So, this negative sign represents that the polarity is this way. Okay. So, this is the basic graph between how photocurrent varies with applied voltage. So, it is pretty easy to understand once you get a proper idea of what is happening inside the tube. So, electrons are coming out with some velocity, and the faster moving electrons will be able to reach. So, even when there is no battery, you can get a current, and if there is a battery with positive polarity, the electrons are pulled in this direction. So, as you increase the voltage of the battery, the current keeps increasing, because more and more electrons will be able to reach the anode. And in the same manner, when I am changing the polarity to the negative side, which is this, the electrons which are coming out will be opposed by the electric field produced by the battery inside the tube, and the electrons will actually slow down, and sometimes even the fastest moving electron might not be able to reach the anode, and this is the point which signifies that. So, this point on the graph signifies that even the fastest moving electron is not able to reach the anode. So, that is the reason why the current drops down to 0, and the value of that negative voltage which we have to apply to make the current drop to 0 is what we call as stopping potential. So, stopping potential is the negative value of voltage applied, so that the current becomes 0, and the reason why it becomes 0 is because even the fastest moving electron coming out is losing its energy before, and it becomes 0 before it reaches the collector. So, that is the basic idea. Okay, so we will now understand the mathematical logic behind this stopping potential. So, I have stated it over here. Let us put that into an expression form. So, at stopping potential, even the fastest moving electron is not able to reach the anode. So, it is being decelerated in such a way that it is stopping even before reaching the anode. So, let me just draw a rough idea of that. So, this is the cathode. Let us say that this is the electron which is coming out, this is the anode. So, because we are trying to find out the stopping potential is related with the fastest moving electron, and the reason for that is pretty simple. See, think of it like this. So, we have many electrons which are coming out from this cathode. So, they have different velocities. This one has, let us say, the maximum velocity. Let us say the one in the middle is the fastest moving electron. So, I can easily say that if the voltage which I am applying is able to stop the fastest moving electron to reach the cathode from reaching the anode, we can say that all the other electrons will also be stopped before itself, because they have even lesser velocity. So, what I am going to do now is I am going to ensure that the fastest moving electron comes to rest even before reaching the anode, and if I write that condition, I would have already ensured that if the fastest moving electron is not reaching the anode, I would have ensured that no other electron will be able to reach the anode. So, that is the condition which I am going to write now. So, we know that the fastest moving electron has the maximum kinetic energy, which is hc by lambda minus phi. So, in this process, if this much of energy is lost even before reaching this particular value, then the fastest moving electron will come to rest, which is what we actually require. So, let us consider that this is connected to a battery with negative polarity. So, like this, and the polarity here is minus, the V naught. I have already changed the direction. So, let us say V naught is the potential, which is the stopping potential. Now, this stopping potential should make sure that this electron with the fastest or the highest kinetic energy will come to rest before it reaches here. Now, let's look at this electron alone. Let us just assume that the potential here is 0 and the potential here is V naught, just for ease of understanding. 0 here and V naught here, which means this electron, when it is over here, is at a potential of V naught, and when it goes here, it is at a potential of 0. So, what that means is that when the electron is going from here to here, it is going from higher potential to lower potential. I want you to remember the earlier concept of potential energy which we have discussed. Whenever an electron goes from higher potential to lower potential, it gains potential energy. Its potential energy increases. It behaves opposite to that of a positive charge. For a positive charge, higher potential means higher potential energy, but for a negative charge, higher potential means lower potential energy. So, as the electron moves from here to here, as it tries to move from here to here, what actually happens inside the tube is that this electron would be losing its kinetic energy and it would be gaining its potential energy. And the reason why potential energy is gained is because it is moving towards lower potential. So, it gains potential energy and it loses kinetic energy. Now, keeping that idea in mind, so now let us say this fastest moving electron has this much amount of kinetic energy. Our idea here is to make sure that this electron does not reach this anode or just reaches that anode. It just comes to rest before this anode. So, what that looks in a real time scenario is that this electron reaches here and it turns back over here and comes back. So, that is what we are trying to make sure happens. So, for this to happen, I can say that all the kinetic energy which the electron possesses at this particular position should become 0 at this position. So, which means it should lose a kinetic energy of hc by lambda minus phi. So, if it is losing this much amount of kinetic energy while going from here to here, what is happening to that energy? It is getting converted into potential energy, and you all know if the electron goes from V naught to 0, its potential decreases by V naught, which means its potential energy increases by E times V naught. We have learned this just earlier in the prerequisite class. So, if the charge of the electron is E and its potential decreases by V naught. So, its potential energy increases by EV naught. So, this is what happens to this fastest moving electron. So, this fastest moving electron starts with this much amount of energy, and all this amount of kinetic energy will become 0 by the time it reaches this end, because all of that has gotten converted into potential energy. So, by the time it reaches here, it comes to rest, and the force due to electric field takes it back once again, not allowing it to reach the anode. So, this is the condition that even the fastest moving electron is not able to reach the anode, and whenever this condition is met, the current in the circuit becomes 0. So, whatever I have shown you in the graph, whatever I have written you here in the definition is ensured by this particular expression. So, hc by lambda minus phi, which is the maximum kinetic energy, is completely getting converted into potential energy before or just before reaching the anode. So, this is the expression. So, now in this particular case, if I make V naught the subject, I will be getting V naught is equal to hc by E lambda minus phi by E. So, we will be actually learning about a graph for this as well, for this expression as well. So, the graph between this is stopping potential, which we have just discussed, the graph between stopping potential and the wavelength of the light which we are using. So, I will draw that graph right over here. Okay. So, if stopping potential is represented on the y axis and 1 by lambda is represented on the x axis, so V naught on y axis, 1 by lambda on x axis. I think you can easily observe that this expression which we have got here is in the form of y is equal to, this is x, 1 by lambda is x. So, it is in the form of y is equal to mx plus c. M here is hc by E, the slope of the graph would be hc by E, and the intercept, the y intercept, this represents the y intercept. So, that intercept would be negative. So, is negative phi by E. So, when I plot the graph, it would be a straight line which is not passing through origin. It has a positive slope and a negative intercept. So, the graph would be like this, and if extended further, it appears to be meeting at a point which corresponds to minus phi by E. So, this width over here, the point where the extended part of the graph meets, is going to give us an idea about phi, the work function of the material, and this part of the graph, you can say that this point of the graph basically represents that photoelectric effect is observed only in wavelengths which are only for the values of 1 by lambda which are greater than this particular value. So, the reason why I have not drawn the graph in this part is because there is no photoelectric effect taking place here. If the value of 1 by lambda is very small, it basically means that hc by lambda is very small, it becomes lesser than the work function. So, this is the point where hc by lambda is equal to phi. So, that is the point where the photoelectric effect takes place, and based on that we also have a definition which we define. We define something called as threshold wavelength. So, threshold wavelength is basically the wavelength below which photoelectric effect can take place. See, now we have an idea that for photoelectric effect to take place, hc by lambda should be greater than phi. So, if I just write that down here, I will show that to you in a while. So, threshold wavelength basically gives us is basically defined as let me write it down. So, threshold wavelength. So, I have told you earlier that you can understand that from the part of the graph here. There is no graph which is behind this in this region. You can say that photoelectric effect will take place or may take place only if hc by lambda is greater than phi. So, if you just write that, if you just rearrange the terms, you would be getting that lambda should be lesser than hc by phi. So, if the value of lambda is greater than hc by phi, then photoelectric effect will not take place, because the photons would become less energetic. Higher the value of lambda, lesser will be the energy of photons. So, the wavelength of the light needs to be below a particular value. So, that is what this basically means. So, this term here is what we call as threshold wavelength. You can define it like this. It is the wavelength, or it is basically the maximum wavelength below which photoelectric effect takes place. So, the wavelength of light needs to be lesser than this particular value hc by phi. So, only then photoelectric effect takes place. You can also define threshold frequency in the same manner by writing, you all know that hc by lambda can also be taken as h nu. So, threshold frequency can also be defined h nu greater than phi. So, you can write it like this, h nu should be greater than phi, or nu should be greater than phi by h. So, in that way we can define threshold frequency as well. So, it is the smallest frequency of the incident light above which photoelectric effect takes place. So, similar to this. Okay. So, that is about threshold wavelength. So, if in this part of the graph we have earlier understood that the slope is basically hc by E, and if you observe here, h is a constant, c is a constant and E is a constant. So, which basically means that if you perform the same experiment of photoelectric effect by using a different material over here. So, this is the material for which we have written the equation. So, if we perform this experiment by using a different material over here, even in that case this slope of the graph which we have got here will not change. So, changing the material over here changes the value of phi and it does not change the value of slope. So, what that means is that even if I change the material over here, I would get a graph which has the same slope but a different intercept. So, it would be something like this. So, if this angle is represented as theta 1 and this angle as theta 2, you can easily say that theta 1 is equal to theta 2. And let us say if this is metal 1, if this is written for metal 1, and this is written for metal 2, I want you to think about which metal would have a larger value of work function. So, I leave it to you, please think about that. Okay, moving on. So, once we have talked about stopping potential and everything related to it, so there is one more very important observation which we will have to discuss about from the graph which we have drawn earlier, which is the reason for the saturation current. Why does saturation current, why does current have to saturate? Saturate in the sense reach a value and not further rise or lower from that. So, it basically becomes maximum over there and it does not change after that in spite of you changing the voltage continuously. So, why does that happen? So, let us try to understand that. So, it is a very important concept. So, I saturation. Now, so we have basically understood earlier that, so when we have this tube, the vacuum tube in which we are performing the experiment, so this is the plate. So, electrons are being ejected from over here and because of placing a battery in this polarity, so the electrons are being pulled in this direction. This battery creates an electric field in this direction, because of which the electrons coming out of the material will experience a force in this direction. So, they experience a force in this direction, and we have discussed that as I keep increasing this voltage, more and more electrons will be able to reach the anode, because even the slow moving electrons initially they get accelerated because of this electric field or the force due to electric field, and even those less energetic electrons might be able to reach the anode, and that is the reason why this current is increasing. We have discussed that earlier. Now, the reason why the current saturates is because if the value of voltage becomes or reaches a particular value, there might be a possibility that all the electrons which are being produced from the cathode are already reaching the anode. So, there is no point in further increasing the voltage. So, I will repeat this once again. The reason why saturation current occurs here is because there will be a point of voltage, or there will be a point at which the electrons which are being emitted over here from the cathode, each and every one of those electrons is already reaching the anode, because the anode has a potential which can pull every electron being produced here. Now, in such a scenario, think what happens if I further increase the voltage? Further increasing the voltage does nothing, because all the electrons which are coming from here are already reaching the anode. So, what is the point of increasing the voltage? And so, that is the reason why you basically observe that changing the voltage does not change the current flowing in the circuit, because from here onwards increasing the voltage has no effect on the flow of electrons. They are already flowing, all the electrons are already reaching the anode, and increasing the voltage just does not help it in any manner. It does not make more electrons come out of it. The number of electrons coming out of it is not controlled by the battery. The number of electrons coming out of it is controlled by the light which is incident on it. So, this light here dictates, or that is the one which puts an upper limit for how many electrons come out of this, and the battery here is just ensuring that all the electrons coming out of it are reaching the anode. So, that is what this saturated value of the graph indicates. It means that every electron is reaching. So, in such a scenario, there is no point in increasing the voltage any further. So, keep that in mind. So, that is the meaning of saturation. Now, if I have to change the saturation current, what should I do? What different ways can I use to change this saturation current? So, let us see that. So, I have just told you here that saturation current arises when all electrons are reaching anode. Okay, keeping that in mind, now if I have to increase the saturation current, the only way I can do that is by creating more electrons, because the electrons which are coming out from here is what decides how much current flows in the particular circuit. When all the electrons are already reaching, there is no role of the battery. The only way I can increase the current is by making sure that more electrons come out of it, and to be able to do so, the idea is pretty simple. More electrons are emitted if more photons are incident. So, it is as simple as that. So, to make sure that electrons coming out of the cathode are more, you will have to make sure that the number of photons which are incident on that material is more. So, simply put, to increase ISAT, to increase the saturation current. So, saturation current will increase if number of photons increases. And from now onwards, to represent the number of photons striking the material, I will be using the term photon intensity or just intensity. So, whenever I say photon intensity or just intensity, for the further discussion, try to relate it with the number of photons striking that material. So, if I increase the intensity, I basically mean that the number of photons striking the material increases. Now, let me summarize whatever we have discussed here about saturation current. First, the reason why saturation current occurs is because there will be a point where the voltage which you have applied is enough for all the electrons being produced here to reach the anode, and once that particular value is reached, further increasing the voltage does not help you in any way, because all the electrons are already reaching. So, the only way you can increase the current or increase the saturation current from there is by changing the number of electrons coming from the cathode, and that can be done by using more intense light, by changing the intensity of light, by increasing the intensity of incident light. So, if more photons are incident on the material, more electrons come out of the material, and those electrons will be carried by the battery through the electric field, and a current is established in the circuit. So, keeping this in mind, let me slightly change this graph. So, let us assume that this is the graph which was drawn in an experiment done twice. In one case, I have made sure that the light incident over here has an intensity of I1, and in the second case, I have made sure that the intensity is I2. So, now one thing you will observe here is that the saturation current in this case is greater than the saturation current in this case, and now you can easily tell the reason why. We have just discussed that saturation current is directly proportional to, yes, it is directly proportional to the intensity of incident light. So, the only way I can change the saturation current is by controlling the intensity of incident light. So, higher saturation current can be obtained with higher levels of intensity. So, the idea is pretty simple. In this particular case, we can directly say that I1 is greater than I2. So, that is about saturation current. So, now I'll just make a table out, whatever we have discussed, all the parameters which we have discussed, I'll just list down them one by one, and I want you to think about all the cases which I am going to write down. So, the observations which we have made in this particular experiment, there are two observations. One is saturation current, which is represented with I sat, and the second one is stopping potential, and it is represented with V naught. And so these are the observations which we have made, and now I will just list down a few factors which we were controlling during the experiment. While performing the experiment, we were controlling few parameters and observing few parameters. So these are the parameters which we were observing, and the parameters which we were controlling was intensity. And once again, keep in mind, by intensity I mean photon intensity, the number of photons striking per unit area per unit time. Okay. B. Next one which we were controlling is the frequency or wavelength, you can say, of incident light. I can change the frequency of incident light or the wavelength of incident light. And the next thing which we were controlling was the work function. Okay. So these are the controllables. So let me just briefly give you an idea of how we can control these parameters. So intensity of light can be controlled by just increasing its brightness. For example, let us say we have a sodium lamp. Sodium lamp sends out light at a particular frequency, and if you just have to make it more intense, all you will have to do is increase its brightness. So increasing the brightness means more photons come out of it. Now changing frequency basically means changing the light altogether. So if you were using blue light, you just use red light or orange, or completely out of visible spectrum you can use X-rays, you can use any other electromagnetic wave. So frequency changing means you are just changing the light as a whole. Variation of intensity means you are keeping the light same, but you are increasing the photons, changing the number of photons by controlling the brightness. Intensity is directly related with brightness of the light. Okay. Now work function can be changed by completely changing the metal on which photoelectric effect is being observed. So these are the controllables and these are the observations. Now I will make a table and I'll stop there for a while, and you pause it for a while, and I want you to fill up that table, and I want you to think carefully about each and every parameter in this particular table, because it is very, very important. So what I am going to do is, I am going to control each and every one of these parameters and observe what happens to these two parameters. So let me write them down over here. In case A is increased, keeping B and C constant, and in case 2, B is increased, keeping C and A constant, and in case 3, C is increased, keeping A and B constant. Now in each of these three cases, I want you to think about what happens to 1, the saturation current, and what happens to 2, stopping potential. What happens to 1, what happens to 2, 1, 2. So these are the conditions. You will have to find out what happens here. So you can stop it here and you can think and answer it. So now in this particular case, let us say I am increasing the intensity. So we have already discussed that changing the intensity changes the saturation current. So saturation current increases by increasing the intensity. I am increasing the intensity. So in this particular case, because of increasing the intensity, saturation current also increases. Now one very important thing which you will have to keep in mind here is what happens to stopping potential. Now I hope you have already gotten it right. Stopping potential does not change, because stopping potential has no connection with the intensity. You can see that from the expression which we have derived also. I will maybe write it down here or here itself. You know that V naught is equal to Hc by phi e, Hc by lambda e minus phi by e. So, nowhere in this expression can you observe stopping potential depending on the intensity of light. So, although I have explained it with an expression, think logically. See, think logically why it does not depend on intensity, why does stopping potential not depend on intensity. So, the reason is pretty simple. See, for example, more intensity means more number of electrons coming out. So, keeping that in mind, stopping potential ensures that the fastest moving electron is being stopped. Now, think about what happens if I increase the intensity. Increasing intensity will make more number of such cases happening. It does not increase the kinetic energy of electron. Let me rephrase it. So, when intensity is increased, let us say earlier there was one fastest moving electron coming out which was stopped. Now, when I increase the intensity, there might be 10 fastest moving electrons. Now, think logically, if one electron can be stopped while coming from here to here by the electric field, you can easily say that even 10 electrons can be stopped. There is no rule that only one should be stopped by the electric field, because while moving in this electric field, whether it is 1 electron or 10 electrons, they experience the same deceleration. So, if 1 electron is being stopped, it means that any number of electrons can be stopped. So, that is the exact reason why the stopping potential does not depend upon the intensity of incident radiation. If it can happen once, if it can happen for 1 electron, it can happen for any number of electrons. So, any number of electrons can be stopped. So, does not change. Then case 2, I am increasing the frequency and I am not changing the intensity or the work function, which means the number of photons striking the metal surface, the number of photons striking the metal surface is the same. The only thing is that now the electrons are more energetic. So, more energetic photons are striking the metal plate. Now, you know that if more energetic photons are coming and striking, the electrons coming out will also be more energetic, which basically means that it becomes more difficult for us to stop those electrons. So, if more energetic electrons are coming out, I need to apply more negative voltage to stop them. I hope you understand that. So, faster the kinetic energy, more will be the potential required to stop them. So, what we can say is that because of increase in frequency, you can easily say what happens to stopping potential. You can also understand from the equation. So, you can write it as h nu by E, C by lambda is nu. So, if nu increases, stopping potential increases, and I have just told you the reason why. More frequency means more energetic photons, means more energetic electrons, means more voltage is required to stop it. Now, what happens to saturation current? So, I told you that saturation current depends on how many electrons are being ejected by the cathode. It does not have anything to do with how fast they are moving or and all that. It only depends, saturation current only depends on the source. How many are being emitted over here, and how many are being emitted over here depends on how many photons are striking. So, in this particular case, because we are not changing the number of photons striking the metal surface, we can say that the saturation current does not change. Okay. Now, case 3, work function. So, we are changing the metal. So, initially we were doing the experiment with a particular metal, and now we have changed the metal altogether. We are not changing any of the initial conditions. So, intensity and frequency are kept the same. So, same amount of light, same kind of light. Earlier, let us say it was being performed on a sodium metal, and now it is being performed on, let us say, a different metal, calcium or some other type of copper, something like that. Now, what happens if we do that? See, first thing, there are two things that can happen here. For example, if you are replacing that metal with a metal of lower work function, then photoelectric effect will continue to happen. But if you replace the metal with a material of higher work function, photoelectric effect may stop altogether, because first condition that should be met is Hc by lambda is greater than phi. So, because you are increasing phi, there might be a situation where this might not happen. So, in that case we can say that no photoelectric effect. So, no photoelectric effect. I hope you understand this. What I have told here is that because we are increasing the work function, there might be a scenario where the light you are using is not energetic to remove the electron. So, that is why I have written no photoelectric effect. But if you are changing the metal and let us say, okay, I have increased this, right. So, when I am increasing this, you can understand what happens to the work function if by looking at this expression, considering that photoelectric effect is still happening even after you increase the value of phi. Even if photoelectric effect is happening, what happens to the value of stopping potential? You can just understand that from the relation over here. By increasing the value of phi, this because of the negative sign over here, the value of stopping potential decreases. So, you can write decreases. And I have told you earlier also, when we need to look at saturation current, so do not worry about work function or frequency. Saturation current is affected by only the intensity, and because intensity is constant in this particular scenario, it does not change. So, understanding this table or making sure that you are understanding each and every one of the 6 points which we have here. So, there are 6 concepts as a whole. So, make sure that each and every one of these 6 concepts is very clear to you, and you are able to give the reason by yourself. So, I want you to think and go through this once again, try to explain each and every one of these 6 by yourself. We will continue.